Position is easy. Position is probably what you think it is. It's the location of an object. Okay, it's just where that object exists. A few things to know about position. First of all, position is a vector quantity. Okay, so in order to define it, you need to choose a coordinate system to measure it in. Okay? If I wanted to know the position of my drink in this room, you guys would need to choose an origin, and you guys would need to choose two axes to define the position of my drink. You could say that the origin is that corner. You could say that this is the x-axis, and that's the y-axis, and then my drink is located some distance along the x-axis and some distance along the y-axis, and that would be its position. And its position will be a vector quantity. Okay? The symbol that we use for position is either going to be x, and remember it's a vector, so it has an arrow over it, or r. Okay, both of those are used to denote position. So if we have an object, and that object exists here, right here in physical space, we would first need to choose a coordinate system. And I could say if I was here, I could say that this is my x-axis, and this is my y-axis. And then the position of this object would just be the vector drawn from the origin of my coordinate system to the location of that object. That's the position. Okay? Another thing to note about position are the units. In this class, we will be using the SI units, this International System of Units. And for position, the SI unit is meters. A notation that I'm going to use a lot in this class are going to be these brackets. If I put these square brackets around anything, this always means the units of whatever I put inside of the brackets. It's just a shorthand notation. So the units of position are meters. Okay? Any questions? Okay. Position, it turns out, is not going to be a really useful quantity because it depends on your choice of coordinate system. Okay? So what the position is, the actual vector that describes the position, changes dramatically based on your arbitrary choice as a human being. Let's say that this person here, we'll say is Alice, starts with an A, and Alice chooses this coordinate system, and Alice measures this position. If a second person, let's say Bob, was over here, and Bob chose this to be his coordinate system, here was Bob's X, and here's Bob's Y, then the position that Bob measures is going to be dramatically different than the position that Alice measures. See, I'll put a little subscript of a B there to denote that that's the position that Bob measures, and I'll put a little subscript of A here to denote that's the position that Alice measures. Those two vectors are not the same size, they don't point in the same direction, they're completely unrelated. Okay? So when we study physics, we're not going to end up using quantities that are heavily dependent on choices that we make as human beings, because physics should be the same regardless of whether we're here or not. The resulting physics should not depend on who makes the choice for coordinate system, Alice or Bob. Physics should be the same regardless. Okay? So there's a related quantity that's more important, known as displacement. displacement is the change in position. Okay? Anytime you guys take a science class and you're describing a change in something, scientists tend to use a specific notation. Do you guys know what symbol we use for change?
Delta.
It's a delta. It looks like a triangle, right? Okay, it's the capital Greek letter delta. Okay, and a change always is measured as the final value of some quantity minus the initial value of some quantity. Change is always the final minus the initial. Okay? So, if position is x or r, displacement would be given by delta x or delta r. Okay? Displacement should be a vector because position is a vector. And if you take the subtraction of two vectors, final position and initial position, the subtraction of two vectors is itself a new vector. Okay?
Can you repeat that last sentence?
The subtraction of two vectors is itself a vector. So when you try to measure displacement, that delta x is going to be x final, the final position that the object is in, minus the initial position where the object starts. The subtraction of two vectors is always itself a vector. So displacement should be a vector. Okay? So let's say that an object starts here at some initial point, and an object ends here at some final point. Okay? If Alice chooses this coordinate system, x and y, then Alice is going to measure a particular initial position and a particular final position. Alice's initial position would look like this. This would be x initial for Alice. So I put the subscript of I and a subscript of A, just to denote that that's the initial for Alice. Okay? And then Alice would measure a final position. This will be x final for Alice. The notation isn't super important as long as it's understandable, as long as it's easily understandable. So for instance, you could put initial and final. You don't have to put them as subscripts. You can put them as superscripts if you want to. Okay? You could also put Alice as a superscript if you want. All right? Or you could use x to denote the position measured by Alice, and you could use r to denote the position measured by Bob. Okay? It doesn't really matter as long as you're clear about the notation. Now let's say that Bob, who's over here, chooses a different coordinate system. Then Bob is going to measure different initial and final positions. So here's the initial position for Bob. Here's the final position for Bob. Notice that the initial position, that vector, is completely different for Alice and for Bob. Different lengths, different directions. The final vectors, different lengths, different directions. But now if we measure the displacement, the movement from the initial point to the final point, the displacement is always drawn from the initial point to the final point. You always draw a vector like that, going from where you start to where you end. So Alice's displacement is going to look like this. There's the displacement for Alice. And Bob's displacement is going to look the exact same, from the starting point to the ending point. It's actually a little bit hard to see how it turned out here. Can you guys see that no matter what, they're going to look the same? The vector's going to be drawn from the initial point to the final point. It doesn't matter what coordinate system you're in. So those two displacements are the same length and they point in the same direction. They are identical. So displacement is a good physical quantity because it's independent of the chosen coordinate system. Okay? Displacement will always be the same. It doesn't matter what coordinate system you choose. Okay? Any questions about displacement? Now, I said that there were two related quantities to position. By the way, just to be clear, displacement is the same units as position. It's still meters. The third quantity up here is going to be distance. Distance is going to be the trickiest out of these three to measure. Okay? Position requires one thing to define. It requires a single location for the object. Where the object is at any given time, that's all you need to know to define that object's position. Displacement, you need two things. You need to know where the object started and where the object ended. For distance, you need three things. You need the initial point, you need the final point, and you need the actual path taken from the initial point to the final point.
What did you say you needed?
For position, you just need to know where the object is located at a given time. So if I wanted to know the position right now, I would say the object is here right now. For displacement, I need to know where it started and where it ended. But I don't need to know how it got from its initial point to its final point. Okay?
Distance you do.
For distance, you do need to know the path. So if this is the initial point, and this is the final point, regardless of how an object gets from initial to final, the displacement is always the vector drawn straight from the initial to the final point. Displacement does not depend upon the path taken. Distance will depend upon the path taken. Okay? The distance is going to be the length of the path taken from an initial position to a final position during some displacement. Okay? So the object undergoes this displacement, delta x. In order to undergo that displacement, it has to follow some path. It can follow a straight path from I to F, or it could follow a curved path. It doesn't have to be straight. So let's say that the path is just some random shape like this. This is the actual path taken. The distance is going to be the length of that path. If you imagine that this path was a piece of string, and you grabbed that piece of string and pulled it taut, and you measured the length of that piece of string, that would be the distance. Okay? In general, how do you guys think distance is going to compare to displacement, to the magnitude of displacement? This vector has some length, it has some magnitude. In general, how do you think that that magnitude compares to the distance along some path? Should they be the same?
Equal or the force? Bigger, equal or bigger?
Bigger than or equal to? Why do you say that?
Because the path could be a straight line,
Uh-huh.
or it could be more like.
Why couldn't it be smaller?
No.
How
I
come?
wouldn't get to the point. No?
Why couldn't the distance be smaller than the length of the
At
displacement?
least know in that case.
Yeah. Because the straight line is the shortest distance. I know that you guys knew intuitively what it
Yes.
was. I just wanted somebody to say it. The shortest distance between any two points is a straight line. Okay, so the minimum distance traveled will always be the magnitude of the displacement. That's the minimum possible distance between any two points. Any path that is not a straight line has to take a larger distance to traverse. Okay? So distance will always be greater than or equal to the magnitude of displacement. I'm being really specific here. This is the magnitude of displacement. Okay? When is that going to be an equality? Remember, this is greater than or equal. When will it be an equal sign? If the path taken is a straight line. Okay? This is only going to be equal if path taken is straight. Okay?
Quick question though. So, but if we measure in meters, isn't the distance the shortest way? So isn't it smaller or equal to?
No.
So how come?
The magnitude of the displacement is just the length of this vector.
Exactly.
Okay? This vector is always going to represent a straight line. So the shortest distance between any 2 points in space will always be that straight line. If you curve away from a straight line, you have to necessarily walk a farther distance. Any curved line is going to be longer than any straight line connecting 2 points.
This is just a requirement that it needs to have for a distance, right? This is
Yeah,
just
they're
a
going to have
requirement.
the same endpoints. They're always going to be across the same endpoints. If you chose a path that was shorter, like this long, it wouldn't have the same endpoints and there'd be a different displacement than this. Right? For instance, if I chose a path that looked like this, that path does not correspond to that displacement because it has different endpoints. That path would correspond, that would have a different final point, that path would correspond to this displacement, but still, the distance along that curved path would be longer than the magnitude of that displacement. Anytime you have a curved path, the distance is going to be greater than the magnitude of the displacement. Always. Okay? Any questions? In general, you guys are not going to be able to measure the distance along curves. Okay? So either the distance will have to be given to you, or the curve will have to be a particular shape. One that you can measure the distance along, and that particular shape is a circle. Okay? You can measure the distance along circular arcs. So let's see an example of that inequality. Let's imagine there was a circular track. So this is X and this is Y. We're going to start here. This is the initial point. And we're going to end here, the final point, and the circular track is going to extend like this. Okay? So a jogger is moving along this circular track. So the curve is the actual path taken. And this path has a radius of 100 meters. What I want to know is what's the displacement and what's the distance traveled. Okay? So first of all, the displacement is always going to be the vector drawn from the initial point to the final point. So that's the displacement. There's the vector drawn from initial to final. Okay? What's the length of that vector going to be? If the radius of that arc is 100 meters, and you go straight
It's gonna be
across.
twice.
What?
Twice?
Yeah, it'll be the diameter. It'll be twice 100. So its length will be 200 meters. What direction is that vector pointing in? The x direction. So if you wanted to write the displacement like a vector, you would say that it was 200 meters pointing in the x direction. Does this vector have any y component? Does it point up at all or down at all? No, it has no y component. So it only has an x component. It points 200 meters in the x direction. Okay? Now, what about the distance? The distance is going to be how long this arc is, right? This arc is the path taken, and that path is going to have some distance. What will the distance along that path be? How would we measure it? It's a circle, and it's specifically half of a circle. Do you guys know what we use to measure the distance along a circular arc? What do we call that? Circumference. If it's a full circle, we would call that distance along the arc the circumference. What if it's half a circle? How do we measure that?
Divide by 2.
Half the circumference, right? So the distance along half of the circle would be the circumference over 2. Circumference of a circle is 2 pi r, so that divided by 2 will just be pi times r. R is 100 meters, so this is about 314 meters. Okay? So what's the magnitude of the displacement? 200 meters. The magnitude is just the length of this vector. This vector is 200 meters long. The magnitude of the displacement is always less than or equal to the distance. So you can see right here that the distance is greater than the magnitude of the displacement. You can see it right here. The distance is 314, the magnitude of the displacement is 200. Okay? Always going to be true. Any questions? All right, let's say that we had a slightly more complicated path. Let's say that this was our initial point, and this is our final point, and I could break my path up into a series of straight paths. So first, you walk 1 meter to the right, then you walk 2 meters up, then you walk 1 meter to the right, then you walk 1 meter up, and then you walk, let's say, 3 meters to the right. Okay, that's not to scale. I'm just coming up with numbers. What I want to do is come up with the distance and the displacement for this path. Okay, how do you guys think we'll figure out the distance? Just add them, right? You walked 1 meter to the right, so that was a distance of 1 meter. Then you walked 2 meters up, so that was a distance of 2 meters. So the distance is just going to be the sum of these smaller distances. Right? So that's 1, 2, 3, 6, 8 meters. Okay? We can call this path 1. We can call this path 2. So I'll call this guy 1, path 1, path 2, path 3, path 4, and path 5. Okay? Each of those paths is going to have a displacement. Okay? The displacement along path 1, hold on, first let me give a coordinate system. Let's say that up is y, and the right is x. The displacement along path 1 is going to be what? The first leg that you walked, what I call path 1. What's its displacement? 1 meter in what direction?
Positive x.
Right.
The x direction, okay? Displacement's a vector, so you have to include the direction. It's 1 meter, I hat. Okay, what about the displacement along path 2?
2 meters to the right.
2 meters in the y direction, so it's 2 meters j hat. What about the displacement along path 3?
1 meter in x direction.
1 meter in the x direction, so it's 1 meter I hat. What about the displacement along path 4? 1 meter in the y direction, so it's 1 meter j hat. And what about the displacement along path 5?
3 meter in x.
3 meters in the x direction, so 3 meters I hat. Okay? I want to demonstrate 2 things with this. Okay? You can find both the distance and the displacement from this information. All of these displacements are along straight paths. So if I wanted to know the distance along path 3, or the distance along path 1, or the distance along path 5, this would be an equality, right? Because the paths are straight. The entire path is not straight, right? The entire blue line is not straight. But if I break it up into 5 smaller paths, each of those smaller paths are straight. So I can say that the distance along path 1 is just the magnitude of the displacement along path 1. And the distance along path 2 is the magnitude of the displacement along path 2. Okay? And I can say that the total distance is just the sum of the magnitudes of the displacements. So the distance is the magnitude of the displacement 1 plus the magnitude of the displacement 2 plus the magnitude of the displacement 3 plus the magnitude of the displacement 4 plus the magnitude of the displacement 5. This is just what I wrote up here. Okay? Because the magnitude of the displacement 1 is just 1 meter, the magnitude of the displacement 2 is 2 meters, the magnitude of 3 is 1, the magnitude of 4 is 1, and the magnitude of 5 is 3. So this is 1 plus 2 plus 1 plus 1 plus 3. This line is exactly the same as this line.
And the change in x, that would be
The displacement along path 1,
above that, the green, down. That's
the
change.
displacement along path 1
Okay.
is just the 1 meter in the x direction that you walk along path 1. Okay? So I can find the distance from this information, and I can find the displacement from this information. The displacement is not going to be the scalar sum of these magnitudes. The displacement is going to be the vector sum. Okay? If I want to find the total displacement, so the total displacement from the initial point to the final point, this total displacement, which is a vector, I can sum up these individual vectors. I can sum delta x1, not the magnitude, but the actual vector, plus delta x2, the actual vector, plus delta x3, plus delta x4, plus delta x5.
That's good.
Okay.
Good question.
Yeah.
Can't we just use Pythagoras for that one if we want to get the displacement?
Well, no, I'm finding the vector displacement, not just the magnitude.
Oh, okay.
But yeah, eventually you can use Pythagorean theorem to find the magnitude. Okay? Delta x1 is 1 meter I hat. Delta x2 is 2 meters j hat. Delta x3 is 1 meter I hat. Delta x4 is 1 meter j hat. And delta x5 is 3 meters I hat. How do you simplify this? Combine what? The i's, combine the j's. But you keep i's and j's separate. Okay? So 1i plus 1i plus 3i is 5 meters I hat. 2j plus 1j is 3 meters j hat. Okay? What I want to illustrate here is something that I had mentioned near the end of last class. If you have a vector sum, right? Like I had said, imagine A plus B equals some new vector C. Then it is not guaranteed to be true that the magnitude of A plus the magnitude of B will equal the magnitude of C. Okay? Just because this is true does not mean that the magnitude of A plus the magnitude of B equals the magnitude of C. Okay? It does not follow that the magnitude of C equals the magnitude of A plus the magnitude of B. Okay, we can see that right here. I summed up the individual vectors and I found the displacement. What's the magnitude of this displacement? We would just need to use the Pythagorean theorem here. The magnitude of any vector is given by the Pythagorean theorem. So this is going to be the x component, which is 5 meters, squared, plus the y component, which is 3 meters, squared. That's 5.83 meters. But compare that to the sum of the magnitudes. What was the sum of the magnitudes? 8 meters. Okay? For vectors, the magnitude of the sum is not equal to the sum of the magnitudes. And that's an important thing to notice.
The sum of the magnitude is not always equal to sum of the vectors, that's what you just said.
Yeah, the sum of the magnitudes is not necessarily equal to the magnitude of the sums of the sum. Okay? And notice once again that I obey this inequality. What's the distance? 8 meters. What's the magnitude of the displacement? 5.83 meters. The magnitude of the displacement is less than the distance. Why is it less than the distance? Because we didn't follow a straight line. Okay? Any questions? Okay. Now we're going to move on to the next kinematic variable, which is velocity. Roughly speaking, velocity is the measure of how quickly an object is changing its position. I'm going to put a little asterisk there. The reason why I put that asterisk there is because this definition is not a useful definition. This definition is a conceptual definition, and it will allow you to understand what velocity means, but it will not let you measure velocity. Using that definition, there's no way to actually determine what the velocity of some object is. Okay? In practice, there are two different types of velocities that you can measure, and they're measured in two different ways. Okay? In practice, you can measure the average of some quantity, and you can measure the instantaneous value of some quantity. Okay? The average measurement occurs between two distinct points in space at two distinct times. So if an object is here at some initial time and an object is here at some final time, you'll measure the velocity by figuring out how far it traveled during that time and dividing that by how long it took. Okay? But an average occurs between two distinct points in space at two distinct times. An instantaneous quantity is a quantity that's measured at a single instant in time. Okay? An instantaneous quantity occurs at a single instant in time. So for example, if you're driving from point A to point B, and the distance is 15 miles, and it takes you half an hour to get from point A to point B, then that 15 miles divided by that half hour is an average of 30 miles per hour. That's on average how quickly you're changing your position. On average, you're ending up 30 miles farther from where you started every hour. But that does not mean that at every instant in time during your trip, you're traveling at 30 miles an hour. Okay? Each instant in time, you could be traveling at a dramatically different speed. Right? At some times, you're going to be at a red light, and your speed will be 0. At some times, maybe you're on a highway, and you're going to be traveling at a much, much higher speed. Okay? And then they average out to 30. The average is always measured between two distinct points in space at two distinct times. The instantaneous is measured at a single instant in time. I'll demonstrate in theory how you guys could measure the instantaneous value, but in practice, this is a physics without calculus class, so we won't be doing it. Okay? No, the instantaneous. Okay? Let me write out a simple equation for the average velocity. First of all, velocity is a vector, and it's given by the variable v. To denote an average, I'll put a little subscript of AV. Okay? The average velocity is going to be the displacement over time. This is for an object that travels from some point A to some point B and takes a displacement delta x, and it takes an amount of time, delta t, to travel from A to B. That would be the average velocity from A to B. Let's look at this problem right here. What if I told you that the jogger can get from the initial point to the final point in an amount of time, delta t is 100 seconds. If that's how long it takes the jogger to get from the initial point to the final point, the jogger's average velocity would be the jogger's displacement divided by the jogger's time. The average velocity would be the displacement over time. The displacement is 200 meters I hat. So I'll put 200 I hat, and the time is 100 seconds. So I'll put 100. 200 divided by 100 is just 2. Okay? The units for velocity are going to be meters, which are the units of displacement, over the units of time, which are seconds, so it's meters per second. So this is 2 meters per second I hat. Okay? What the average velocity measures is on